Hi, this is topic number 3, electrical quantities and units and fundamental concepts. So it turns out we have physical, electrical, and magnetic units of measurement. There is the International System of Units, what's called SI, and there's fundamental and derived units. So across the world, scientists have agreed on fundamental units of measurement. This chart indicates those fundamental units to my left. So for length, we tend to use the meter. That is the recognized unit. The symbol is little m. For mass, the unit is kilogram. The symbol is kg, little kg. Time is second, and the unit is small s. Electrical current is the ampere, capital A. Temperature is in degrees Kelvin, which is capital K. That's something you may not be familiar with because most of us use either Celsius or Fahrenheit. Luminous intensity is the candela, or small CD, and the amount of a substance is called the mole, or small mol. So in this picture we see a meter and a yardstick, meter stick, yardstick, a foot-long ruler, and a measuring device. So it turns out the basic unit of length is the meter, and it's about 39 inches long. A yardstick, as you're probably aware, is 36 inches, and a ruler is 1 foot or 12 inches. And the tape measure would probably have units of feet and inches. So it turns out that the kilogram, our unit of mass, is a fundamental unit. Kilograms approximately equal to about 2.2 pounds. In the United States, we tend to use pounds all the time. And as you could deduce, drug dealing, which is an international activity, uses the kilogram as a unit of measure. So this shows a kilogram sitting on a pound scale and about 2.2 pounds per kilogram. Now, the international standard for kilogram is shown here in this picture, and you can see the standard is kept in dual, glass containers, I guess you'd say. I believe it's made out of platinum. It's at the center there, and it turns out you have a covering of one glass covered by another glass, and it may actually be vacuum in a vacuum. Who knows? But it turns out that's the standard international kilogram. So when we talk about time, we use the second, and it turns out that the agreed upon unit of time being a second, there's a time standard, and it's created by an atomic clock. Time certainly is an elusive unit, in a sense it appears to change as one ages, and that sense should be S-I-N-C-E, so I'll have to change that in the slide. So in the time standard, we have atomic clocks and network synchronization. So atomic clocks are defined by International Atomic Time, and there's something called the Stratum 1 frequency reference in telecom networks. We have the Global Positioning System, which uses atomic clocks, and we have scientific clocks. So there's important network synchronization that occurs. Matter of fact, if you look at your laptop or whatever device you might be on now, it turns out that there's network time pushed out to you over the network. So your smartphone, as well as any of your portable devices, will always have the same time basically on them. And again, it's important to have network synchronization for telecom, power grid, electronic, financial transactions, and so forth. So you have some pictures here. On the far left, you see a network. Then you have a picture of the whole world. You have a picture of Wall Street, and you have a picture of transmission lines for electricity. You'd be surprised, Wall Street, you can make money by being the first one to buy something, and so it turns out people have gone to all links to take and be able to get their transactions to Wall Street before somebody else does. So time-sensitive networking is something that's relatively new, and today, due to computer networking applications, we need to build time-sensitive networks. So this graphic shows a time-sensitive network switch. It shows inputs coming into a switching fabric, and it turns out that some of them will have priority over others, and there might be a schedule associated with global time, and again, various outputs from that switching fabric might have priority over other things. If you think about automatic emergency braking systems for automobiles, you certainly would like to give a priority to that type of traffic. If there's a message that comes in and says, hey, you should brake so you don't have an accident, as opposed to other types of traffic. So let's switch our gears here a little bit to talk about electrical things, and the ampere is our electric current standard, and current is equal to the flow of charge. Here you see a blown up wire. There's a cross section A, and there's electrons, which are represented by the circles with a Q inside to indicate charge, and they are passing through that area A. So electric current is defined as the rate of flow of electrons. 1 amp is equal to 1 coulomb per second passing a given point. That is a definition of an ampere. This slide is kind of an interesting one. It's all colorized, as you can see, and it turns out that's a picture you might get from an application that takes and translates temperature into different colors, or what we call colorization. And Kelvin is our unit, but we always use Celsius and Fahrenheit. Fahrenheit, the United States, and Celsius in most of the European countries. Kelvin is related to Celsius. So here's a picture of a camera that actually has, it's a smartphone app that actually has a infrared fiber, I'm reading it, FLIR, which is some type of infrared camera attachment to the smartphone, and it's showing looks like the hot water coming out of a faucet. So we switch gears again. Luminous intensity is the candela, and here it shows a light source, and notice that the light is radiating in all different directions. So we've got like a hemisphere over that light source. There's this distance d to the surface, and it turns out that it shows a 1 square meter on top, and the light receiving the surface at some distance d at a solid angle a is related to the candela. A little bit further here, again shifting gears, there's something called the mole, which is the amount of a substance. So chemists use the mole as a measure of the number of particles of a substance. So a chemist's definition of a mole is that 6.022 times 10 to the 23 particles. And those particles could be atoms, molecules, ions, formula units, particles of a substance. And again, there's a graphic there, and it shows the number of molecules, it looks like in some liquid, the number of atoms in looks like copper wire, and the number of particles in some type of looks like a compound there. Okay, so moving along here, now we kind of talk about derived units. So in electrical and magnetic world, we have some derived units, but before we get to those, let's take a look at the quantity on the left here in this chart is an angle. The unit is a radian, and the symbol is R, small r. For a solid angle, we have the steradian, and the symbol is small SR. So radians are used when doing calculations involving sine waves, and steradians are typically used when doing calculations involving antenna patterns and laser beam intensity. So it would turn out that in the laser world, steradians are used as well as radians quite commonly. So here's a picture of the radian, and it turns out that we have a circle, and everyone knows that the circle has a radius, and it has a diameter, which is 2 times the radius. Also has a circumference. So the radian is defined as the angle which subtends the radius of a circle on its circumference. And there are what are called 2 pi radians in a circle. 2 pi radians would be 360 degrees if we did it angular. So it turns out that there's a relationship between radians and angle. It's about 53 degrees per radian. Steradian, you can see in this picture, is it adds an additional dimension to the radian, and so it turns out here's a globe, and the globe is 3-dimensional. It's got a radius, and it turns out that the steradian looks like you take looks like a radian, and you take the area of what it would be on the surface of that sphere. And units of energy. It turns out that we have SI units of energy, and the SI unit of energy is a joule. You don't use that too often, but we talk about the power output of lasers as in being in joules. So a joule is 1 kilogram per meter squared per second squared, which is equal to 1 Newton times meters. And a Newton is the unit of force. So it's equal to mass times velocity squared, mass times the constant of gravity times the height on Earth, and G is equal to 9.281 meters per second squared. For an ideal gas, there's another equation here. Power is energy per unit of time. So 1 watt is equal to 1 joule per second, which is equal to 1 kilogram times a meter squared per second squared. That's used mostly in electricity, but also for vehicles and horsepower, acceleration, time, and so forth. So finally, here's a big, very busy chart of electrical quantities, symbols, and derived SI units. So most electrical units are derived from the more fundamental units. So for capacitance, we use the symbol C, and the SI unit is farad. The symbol is F, capital F. For charge, we use the symbol capital Q. The SI unit is coulomb, and the symbol is capital C. And of course, we just talked about current being a coulomb per second. For conductance, we use the symbol G. The SI unit is Siemens, and its capital S is the symbol. Energy, the symbol is W. The SI unit is joules. The symbol is capital J. For frequency, frequency being the number of cycles per second of a sine wave, the symbol is lowercase f. The SI unit is hertz. Hertz is cycles per second, actually, and the symbol is capital H, small z. For impedance, we use capital Z. We use ohms for impedance, and the symbol is omega, capital Greek omega. Inductance is capital L. We use Henry as the SI unit, and it's capital H. Power is capital P. We use watts, and the symbol is capital W. For reactance, reactance is the value of capacitance or inductance has to AC current applied to it. The symbol is capital X. We tend to use capital X with a lower L for inductive reactance, capital X with a lowercase c for capacitive reactance. And the symbol for that, the SI unit, is ohms with omega again. Resistance is capital R, ohms, and omega. And voltage is capital V, volts for the SI unit, and capital V. So those are all the fundamental and derived, well, I should say derived SI units. So this diagram here is real interesting. It shows a bunch of different types of capacitors. So what are capacitors? Well, you got a picture of them here. There's looks like 2 wires coming out of each one of them. So it has 2 leads, and it turns out it's 2 conductors connected to those wires, but they're separated by an insulator. And this diagram shows different types of capacitors. What do capacitors do? They store energy in electric fields that exist between the 2 metal conductors that form the capacitor. And again, those 2 metal conductors are connected to 2 leads that go to the outside world. So this electric field takes time to be created, and thus the capacitor is said to charge and discharge as voltage is applied or removed from the capacitor. And there are today things called supercapacitors, which are used in various transportation devices. This picture shows inductors. And inductors have many different shapes, as can be seen here. Inductors store energy in the magnetic field that builds up around the coil windings. Like a capacitor, it takes time to either energize the magnetic field or collapse it. Thus, the current through an inductor cannot change instantaneously. The inductor, like the capacitor, has a time constant, it's called, associated with its operation. And we'll get to that later on. Now, this one shows the other third component that we talk about in electronics usually, and that is resistors. And you can see there's many different types of resistor packaging, leads and mounting styles. There's carbon and metal film resistors, thick film resistors, thin film resistors, wire wound resistors, special purpose resistors, and adjustable resistors, or sometimes called potentiometers. Now, what do resistors do? They oppose the flow of current. The bigger the resistance value, the less the current will flow. Resistors can be used to create new voltages in a series circuit or to limit the amount of current through a component like an LED, for instance. This next chart shows magnetic quantities, symbols, and derived SI units. These symbols are not as commonly recognized as the electrical ones, but nevertheless, they're what we use today. So I'm not going to harbor much time on them, but let's take a look. Magnetic field intensity has the symbol H. The SI unit is very complicated here, ampere turns per meter, and the symbol is capital A, small t, divided by an M. Magnetic flux has a symbol of phi or phi, however you want to use that Greek symbol there. It's called Webers for the SI unit, and symbol of W, small b. Magnetic flux density is B, or Teslas, and the symbol is capital T. Magnetomotive force is capital F, small m. Ampere turns. Permeability is mu, Greek letter mu, which is a real complicated SI unit. And reluctance is a script R. So these things, again, are not as commonly recognized, and they're kind of, I guess you'd say, you'd look them up as you needed them. So magnetic fields, as we see in this diagram, a permanent magnet will have magnetic fields. Bar magnet shown in the top left has the south and north pole, and you notice that the magnetic field starts and terminates on the north and ends up on the south pole in that case. Magnetic fields are complete loops, by the way. The horseshoe magnet shows another way the magnetic field might look. An electromagnetic field generated by a battery applied to a coil has a different orientation than magnetic fields. We also know probably from our childhood that unlike poles attract, if you have two magnets, you might notice that the north and the south would actually attract one another, where if I put the two north poles together in the bottom right, they actually repel one another. Now, that brings us to scientific notation. It turns out that, the people who developed the theory of electronics and electricity and so forth, they were working without knowing, what was happening in the future, and it turned out that they, named some of the basic units, and they were either very large or very small. Well, what's happened is we've had to use scientific notation to deal with their original values that they created, and it turns out powers of 10 is a form of shorthand notation we use. So if we have large or small numbers, again, dictated by what people came up with for the units of, say, capacitance, inductance, and so forth, we might have to use a power of 10 to take and talk about it. So here we see 10 to the 6th is 1 million, actually 1 followed by 6 zeros. 10 to the 5th is 100,000, 1 followed by 5 zeros. 10 to the 4th is 10,000, 1 followed by 4 zeros. 10 to the 3rd is 1,000, or 1 followed by 3 zeros. 10 squared, or is 100, or 1 followed by 2 zeros. 10 to the 1st power is 10. And to make the mathematics work, 10 to the 0 is equal to 1. Anything x raised to the 0 power is always equal to 1. That's to make it so mathematics works. The numbers work out. On the right-hand side, you see 10 to the minus 6, which is a point followed by 6. Well, the decimal point is moved over 6 places. 10 to the minus 5th, the decimal point is moved over 5 places. So 10 to the minus 6th is a millionth. 10 to the minus 5th is 100,000. 10 to the minus 4th is the decimal point moved over 4 places, or 1/10,000. 10 to the minus 3rd is a thousandth, or a decimal point moved over 3 places. 10 to the minus 2 is the decimal point moved over 2 places, or 1/100th. And 10 to the minus 1st is 0.1 or 1/10. So that's all the scientific notation, and of course the numbers can go very high or very low. So some examples of the use of scientific notation. Depending on your background, you may want to go over these. There are some examples. Example number 1 here says express each number in scientific notation, and it has the answers written out. Example 1-2, express each number in scientific notation, and it shows, for instance, like 0.2. Well, 0.2 would be 2 times 10 to the minus 1. And again, they're all worked out for you. So again, you may want to look at these, or may not have to. Here's another one, example 1-3, says express each of the following as a regular decimal number, and it has the solutions worked out for you. So you might want to go over those again as you need. Now, it turns out engineering notation, metric prefixes, we take and use engineering notation is limited to powers of 10 that are multiples of 3. So what happens is we can take, in this example, for instance, it's got part A, express the following numbers in engineering notation. So 82,000 becomes 82 times 10 to the third. 243,000 becomes 243 times 10 to the third. And the last one, 1,956,000 becomes 1.956 times 10 to the sixth. Now, the reason why we do this is because we can use metric prefixes. So in this next slide, which, well, just another example. So in this case, the use of powers of 10 that are multiples of 3 give rise to metric prefixes. Metric prefixes, more shorthand. So these are all negative metric prefixes. So now we go to this table here, and this shows what we have for the metric prefixes. So again, this is circa 2020, a couple of years ago, and ones that are commonplace are, if we take a look at centi or C, it's 0.01, say hundredth. Milli is 0.001 or a thousandths. Micro is 0.00001 or a millionth, 10 to the minus 6th. Nano, 10 to the minus 9th or billionth. Pico, 10 to the minus 12th or a trillionth. Then we have femto, 10 to the minus 15th or a quadrillionth. And the other ones you won't recognize probably. Atto is 10 to the minus 18th. Zepto, 10 to the minus 21st. And yocto, 10 to the minus 24th, which is a septillionth. On the other scale, getting bigger, deca is a factor of 10. Hecto is a factor of 100. We don't use those too often. Kilo is a factor of 1,000. Mega is a million. Giga is a billion. Tera is a trillion. We tend to use that now. Terabytes of memory. Peta is 10 to the 15th or a quadrillion. Exa is 10 to the 18th. Zeta, 10 to the 21st. And Yoda, 10 to the 24th or a septillion. And, you know, it turns out as we take and we get better at measurements and so forth, and we can take and do more with our instrumentation, we actually come up with new prefixes. And again, when I was a young person, things like pico is represented as micro, as opposed to pico. So, you know, femto, atto, zepto, yocto, and all these ones with the peta, exa, zeta, and yoda, which you don't hear too often, have become new to the vocabulary. Notice that everything that's small is a lowercase, starting except when you get up to mega, then everything is a uppercase as you go the other way. Okay, so there's some metric unit conversion examples here, so I'm not going to go over them, but example 111, 112, and 113 give you some examples of converting, say, 0.15 milliamperes to microamperes. Example 113, convert 5,000 nanometers, 5,000 nanoamperes to microamperes. So you want to go over those if you're not familiar with this. And here's some more examples. Example 114 through 116, doing some more metric unit conversions. And the last one here, 117, again, more metric unit conversion. So as a review of all this, there are basic electrical and magnetic quantities, and there are international symbols and units. However, because of the vast range of what we encounter in the electronics world, we use shorthand notations. Some of those things are scientific notation, where we use powers of 10. Others engineering notation, where again we use powers of 10, which are multiples of 3. And then the metric prefixes, and again I mentioned new ones become common terms as technology marches on, and our ability to measure things, both large and small, improves. So that is the end of this little discussion about